Yes. Let's begin with the word of prayer. All right. Dear God, thank you for this day, and thank you for the opportunity for us to study algebraic topology. Pray that you'll just give us clear minds and help us to understand everything that we're studying. In Jesus' name I pray. Amen.
Amen. It's a good thing you're doing it today, because I definitely couldn't today.
Yeah. We'll find out if I can do it. So today we're going to be talking about excision, and so I was kind of just like looking for a pun to do about excision, but I couldn't really think of any, so I just cut it out.
Cut it out.
Thank you, everybody. I'm thinking. And so we have these. So we're looking at these two different kinds of excision, or are they different? We'll find out. So the first one is as follows. First one is if you have these space X with these two subspaces, U and A, with U subspace of A, and U, the closure of U is a subset, or yeah, the subset of the, what's it called?
Interior?
Interior, yeah, that's right. Sorry, I'm trying to blank. Okay, of A. Then the inclusion that maps this top two, x minus u, a minus u to xa, induces the isomorphisms for each n from hn of x minus u, a minus u to hn of xa. And we also have another excision, which actually for the first one I'll kind of just talk about, draw a little picture for that, since I think that's pretty instructive. Just kind of getting an idea. So we have this space X with a subspace A. We also have another subspace U. And so this excision, if it's true, which I hope it is, says that the relative homology of like XA is the same as x minus u, a minus u. So just taking out this u out of both of them doesn't change the relative homology. Okay. And here's another excision that looks very unrelated in terms of, so these two different subspaces, x1 and x2, where x is going to be equal to the union of the interior of x1 and the interior of x2. And so we have this other property where the inclusion that maps x1, x1 intersect x2 to x1 union x2, x2, which x1 union x2 is equal to x, so it's the same thing. So this induces isomorphisms J star from the homology groups to homology groups. So yeah, that's cool. So let's prove that these are the same thing.
So the second one, again, the idea of the second one is you've got
So like if you have this
two
you have
subs.
x, then you have like, for example, x1, then you also have, I don't know, like x2. Maybe I should draw a different, use a different color for this one. Yeah. x2, then the relative homology of x1, x2 is going to be the same as x2. So kind of like
X and X is the union of the interiors.
Yeah. So kind of like taking, like the intersection with x1 doesn't really change the homology group, at least to my understanding. So it's reminiscent of the second isomorphism theorem, because they both involve two subspaces of x. Alright, so let's prove that these are the same thing.
Huh. I guess the first one's sort of reminiscent of the third isomorphism theorem? I don't know. Like the canceling fractions thing in some sense.
Yeah, a little bit.
But I'm just being silly.
So if you look at this, most of the argument for the proof of this is really just kind of like regular topology stuff. But let's go through it then. Okay, so let's start the first. So assume Excision I. That we do have this inclusion-inducing isomorphisms. Okay, and say that x equal interior of x1 union interior of x2. Kind of starting off to prove this one. Okay, and so we're going to define our A and U. Okay. This is first we claim that U bar is a subset of interior of A. Okay, so to prove that, it says interior is subset of the actual space. Makes sense. Implies, let's look after this, that x minus x1 can be a subset of x minus x interior of x1. Which, it's pretty straightforward.
Yeah.
Hence, U bar is equal to x minus
No.
x1 bar.
U bar, is that the closure of U or what?
Yeah,
was
the closure.
Okay.
Which is a subset of x minus interior of x1. Because x1 interior of x1 is open, so this is going to be closed. So the closure of this is going to be a subset of that. The closure of this is being a subset of this means that the closure is also going to be a subset, because it's about as close as it gets. But x minus x1 or interior is equal to interior of x2 union interior of x1. That's x.
Right.
Minus interior of x1, which is equal to interior of x2 minus interior of x1. Because the
Yeah.
the complement gets rid of the union right there,
Huh.
which is equal to the interior of A. Oh wait, sorry.
Maybe I should
Just
put
kidding.
I should put that on the abstract test next Wednesday. See how they do.
Oh yeah, it's so much algebra going on there. Which is a subset of x2, which is equal to.
Alright, there's algebra somewhere there.
Oh my goodness, I have no concept of room. Just take a complement of this is a subset of x2, but since A is x2, then the interior of A is equal to the interior of x2. Okay, second, x minus u is equal to x minus x1. So that's what u is, which is equal to x1. And a minus u is equal to x2 minus x minus x1, which is equal to, this is just by definitions of relative complements, x minus, sorry, not minus, intersect x1 complement. Should I explain that, or this first complement comes from here, the second complement comes from this one.
Oh. Huh.
So this is equal to, oops, intersect x1.
So the second complement applies to.
So there's two relative complements here.
Oh, excuse me.
So it's x2
Oh, okay.
intersect the complement of this.
You know my love of parentheses. I might put a second unnecessary parentheses, but it's cool. It's cool.
Here.
It's fine. It's fine. I mean, it's fine.
I'm not talking about the complement of the whole set.
Yeah. Yeah, you're right. I can't do it. Yeah, where would I put it? I rescind my. I will cut out my.
So it's an order of operations.
My request for
here.
parentheses. I'll excise it.
Yeah. X
I think
minus
the level
u.
of my comedy is where it needs to be today.
A minus u
Very disappointed in myself.
is actually going to be
It's
equal
capped.
to
I already had some.
reusing
Thank you.
what we had before. So that's equal to x1. This is a 1. This is a comma. Okay. So we're well on our way. So now we have this set. Okay. And then here it says that xa is equal to x2. So the inclusion from x minus u, a minus u to xa is the same thing as the inclusion from x1 intersect x2 to xx2, which is precisely the so these inclusions are actually the same thing, and thus this being isomorphism makes this also an isomorphism. So like.
So really, I mean, in summary, these are really just set theoretic.
Mm-hmm.
They just look the different at first glance, but really set theoretic. These are just set theory arguments you're giving.
Right. Exactly.
Show that these are equivalent characterizations of.
Mm-hmm.
It's like doing the limit with h versus x minus a or something, you know.
Mm-hmm. All right. So that's the first part. So let's do the second one.
Mm-hmm.
Let's do the second one. So it's a little bit shorter. I think. Yeah. Okay. So we start with for Excision I, we have these two subspaces with closure of U, subset of interior of A, and define x2
I
equals
can't
A.
see Nathan on my end. You have to.
Oh yeah.
I'll take care of it.
Yeah, this is really kind of like a mirror of the other one. Alright, define x1, x2. x1 equals x minus u. Okay. So u is a subset of closure of u. Good start. Which is a subset of the interior of A. So that means that x minus u contains, I'm just going to do x minus A interior is a subset of x minus u bar, which is a subset of x minus u. Really good at that. X minus u bar is open since u is closed. That means that, okay, x minus u bar equals x minus u bar interior, which contains x minus interior of A. Hence, so we're trying to show that we have the initial property for, or trying to show that these definitions of x1 and x2 have the initial property that we have in Excision II. So that's equal to x minus u is a subset of x minus u bar interior. Or wait, yeah.
Or a superset, actually.
This
Right?
Right, yeah, you're right, superset. You're right. Okay, union. Interior of A, which is also a superset of x minus interior of A. I probably shouldn't have changed it. Oh well. X minus A union, or x minus interior of A union interior of A is equal to x. So we're good, we have that, and that's pretty much what we need for that.
Well, if they like to think in terms of subsets, they can just read it Manga style, you know.
Yeah, exactly. It says, finally, it is easy to see that x1 intersect x2 is equal to x minus u, a minus u. Pretty much, like I said, these are pretty much defined the same way as we did for the other proof, for the proof of the other direction, so it's the same thing, and x2 is equal to xa. Therefore, the inclusions are the same, therefore, the isomorphisms are the same, and therefore, you know.
So we could either think of excision. Huh. I guess he uses both for depending on the.
Yeah.
Yeah.
But he uses the second one to kind of prove it, or when he proves it.
Okay.
Okay. And now he says that we are going to prove it eventually, but first we're going to look at some of the consequences. So, which are some pretty sweet consequences. So let's go into that. I think hopefully we all kind of have a good idea of what excision is because I'm erasing this. So, how much diagram chasing do you guys want to do?
All of it. No.
All of it.
Enough until we get bored with it.
Yeah, I did all of it, but
It's
there's
dangerous.
there's like 6 steps, and so I might only do 2. Kind of get an idea of what we're looking at. So look at this diagram lemma. Okay, so if we have a commutative diagram, with exact rows, because who wants diagrams about exact rows? Okay, so we have and back to an, or a minus 1 that is. If I miss any of these,
Do you feel like you've done enough diagram chasing that you've reached your maximal efficiency?
I haven't really written any of these on the board, so I don't know. What do you mean, like the actual process of diagram chasing?
Yeah, I mean, like, are you?
I hope so. It's pretty fun when you actually work through it. Qn and what a curveball delta. Okay, we also have minus 1. Hn.
Ran out of letters, huh?
Yeah. And then, all right, so.
I mean, he could have used a prime, but he just decided he didn't like primes, that he typed this up.
With
I mean, he's still using some primes, so.
Hn and isomorphism.
See a prime in the next thing. Oh, you're right. The whole thing,
Run.
the whole lower rung there has got primes on it. Yeah. A and prime, B and prime Cn prime.
So every third of these maps is every Hn or H, for all n is going to be an isomorphism. Okay.
Ooh.
Then
Oh, that's assumed?
yes,
That's assumed, yeah.
exists in an exact sequence. Kind of like not really intuitive sequence in my opinion.
Huh. Oh, the difference of Gn and J.
Yeah.
That is surprising. Oh, that's what? Can you?
He explains what that is.
That seems like a dangerous subtraction.
Mm-hmm. 2 n-1, etc. Okay,
So you can
we're
subtract apples from oranges as long as you got the proper interpretation, is what we're saying.
where in Fn maps.
Well, you're subtracting apples and oranges in the sum of apples and oranges.
Oh, yeah.
We're,
You got a good point there.
we're subtracting the maps
Right.
of apples onto pears and oranges on pears into pears. Okay. Goes from maps AN to INAN
Uh-huh.
and FNAN. Makes sense. And
Ooh.
like I said, GN
Sneaky.
minus JN maps elements of BN direct sum AN prime.
So in his defense, that's what it has to mean, I guess.
GN BN minus JN AN prime. Okay. Prove the exactness is a diagram chase. So which one do you guys want to show? Which part do you want to show as exact?
I'd be interested to see how it's shown for the first part where you have the direct sum.
Like,
Yeah.
So right here.
Right.
This one's the best one.
I've chosen wisely.
All right, let's start. So first, we'll start with the easy part.
First, fresh marker.
Okay. Want me to throw this away?
Yeah, go for it. I think it's
Actually,
lived to.
I'll keep it.
Oh, you keep it? Alright.
Yeah, I'll keep it.
Very kind. I think I would have.
Alright, so first, we're going to be focusing on this one. Okay. So first we'll show that the image of INFN is a subset of GN minus J.
That's good. Sorry.
I might start taking off these indices. That's not really useful. Okay. So so I'll just take off the ends since it's all n here. Be a prime, be an element of the image of IF. Okay. That means there exists an element of and such that be a prime is equal to IF of A. Okay, we good there? That's just definition. So what is G minus F of B A prime is going to be equal to GB minus F A prime, which is equal to GIA minus minus JFA. Okay? But what do we do? Oh, because they're the same thing, right? Because GI is equal to JF. I knew it was easy. Okay. Second one, a little bit more elaborate. Show that the kernel of G minus J is a subset of image of IF. Okay. And it might be a little bit sloppy here because we actually will go into some -1s, but forget about it. Okay, so let's be A prime be an element of the kernel. Okay, so that means that GB minus JA prime is equal to 0. Okay, and so because this is equal to 0, we're gonna do Q of this side is equal to Q of this side. So QGB minus QJA is equal to Q of 0, which is 0. Okay, you guys get there? But let's see. QJ is going to be 0 because of the exactness of B. Okay. So that means that QGB is equal to 0. Okay, but QG is equal to HP. Right, HP, QG, all the same thing because it commutes. But H is an isomorphism, so that means that PB is equal to 0. P is an element of the kernel of P. B is an element of the kernel of P. Therefore, by exactness, B is an element of the image of J. Wait, kernel of P, image of I. So that means there exists an element of A such that B is equal to IA. Hey, that might be a good candidate to use. We'll find out if it works. Spoiler, it doesn't. Alright, so where are we? So let's go back to what we had up here. So we have GB minus JA prime is equal to 0. So that means that since B is IA, GIA minus JA prime is equal to 0. But GI is equal to JF, so that means that JF A minus JA prime is equal to 0. Okay, so that means that J of FA minus A prime equals to 0, which means that JA minus A prime is only the kernel of J. No.
FA.
FA.
It's 3 o'clock p.m.
Which means that it's an element of the image. This diagram chasing it's so natural. Okay. FA minus A prime is an element of the image of delta. So that means exists C prime element of C prime such that FA minus A prime is equal to delta C prime. I need to stop doing this. Okay.
Working yourself into a corner.
Yes. But delta is actually equal to H inverse DF, or FD H inverse, because H is an isomorphism. So that means I'll sit down in this nice chair. FA minus A prime is equal to FD H inverse C prime. Okay. Move things around, that means that A prime is equal to FA minus FDH inverse C prime. Oh, but now we have a different element of A, so it's an element of A, such that this maps to A prime. So this actually looks like a better candidate. Let's see if it maps to B with respect to I. Can you still see down here?
Yeah, I moved.
Yeah.
Okay, I,
You're fine.
I of A minus DH inverse C is equal to IA minus IDH inverse C. ID is equal to 0 because of exactness. is equal to IA is equal to B. That means that BA prime is equal to IF of A minus DH inverse C prime, which was an element of A. So that means it's an image of IF. So we have exactness there. The other ones are pretty similar. I thought that was really cool.
Yeah.
It's you kind of go like all over the place for that one, so I like that.
But you discover the need for the isomorphism in the midst of it.
Right, you actually need the isomorphism for every exactness part, I think. Yeah.
So he mentions this is from Barrett and Whitehead. Apparently, this level.
Alright, so now we can prove. Okay, so how do you pronounce this? Mayor
Viatoris is what I
Viatoris?
heard. Yeah.
Let's look at this.
I'm sure I'm saying it wrong.
Let's
I'm not sure I'm saying it wrong. Well, it's the same way it was said wrong for me, so, I guess it's okay, right?
What language is it?
Language.
Yeah, like-
Topology.
No, I mean like
Like what country
Like,
is
yeah.
Viatoris from?
Oh, that's a good question.
Okay, so we have. If again we're not trying to prove any excision, this is actually going to we're going to use
Vitor
this to find.
Careful of the chord.
Court?
Careful of the chord, I saw it move.
We're going to use it to prove some neat things using excision.
These are Austrian mathematicians, Walther Mayer and Leopold Viatoris. In fact, if you can trust Wikipedia, and I do. Whoa!
What?
Leopold Viatoris on his 110th birthday.
What?
Dang!
Wow.
Dude doesn't look a day over 90. Huh.
In retrospect, maybe that diagram chase wasn't the best idea, but I had fun doing it, so.
So he's one of the people whose work led to the monumental work by Eilenberg and Steenrod. Like the things he did kind of paved the way for them seeing it. Oh, there are many beautiful pictures in this Wikipedia article. Huh. Wow.
Where I1, I2, G, and J are all inclusions. And D kind of defined the same way. This is that equal to D. Each inverse.
Viatoris was born in 1891 and died in 2002. World War I veteran. Earned his PhD in 1920. Sorry, I will keep interjecting. It's fun trivia as you go on. Huh.
You're right, it's G, but it's Q. Here's just defining all the different mappings whose induced mappings we look at here. Okay.
Huh.
Next one. Next two. All right. So these will all make a lot more sense in the proof when we draw the diagram. basically this theorem says that we get this exact sequence. Very similar to the one in the lemma. So we have x1 intersect x2, set x2, times x empty set.
This trick of the empty set is really it's really funny. Huh. I guess it's all relative though, right?
So let's see. So Q is the inclusion here, H is the inclusion here.
Huh.
I1 is the inclusion here, I2. What's this? This is G. G is the inclusion here. Alright. By theorem 5.8, this gives this gives a community diagram. I don't really want to draw it. I guess I can, yeah.
Is this picture on page?
Page 108.
So you've already drawn the top diagram.
Yeah, and then the bottom one that they draw
Yeah.
is basically this, with an being hn of x1 intersect x2, bn being hn of x1, cn being hn of x1, comma x1 intersect x2,
Uh-huh.
an prime is hn of x2, bn is hn of xn, of x, and
Uh-huh.
c prime is hn of x comma x2. And if you weren't able to follow that, it really is kind of like
And then
working backwards.
and then he says that the you get that you need HN as an isomorphism,
Yes.
and he said that's tantamount to what was it? Why is the analog of HN an isomorphism?
From excision 2.
From excision 2. Because we're assuming
Because H goes from x1, comma x1 intersect x2 to xx2. Yeah.
yeah, over here. I can't tell.
No.
This HN induces isomorphisms by excision 2. And so basically that gives this exact sequence, which proves the theorem. Okay.
Huh. So it's connecting the homology of the intersection of two spaces to the direct sum of the homologies. The X is the union of the interiors, right? Huh.
This neat connect sequence.
It's very interesting.
You guys want to look at an example or?
Ah.
Yeah, an example.
Mayer served as the assistant to Albert Einstein. He was nicknamed Einstein's calculator. Born in 1887, died in 1948, 10th of September.
Okay, so this is an example of where excision wouldn't work because we don't have the required properties. So it's an example of where x equals x1 union x2, but not the union of the interiors. Okay, this is a kind of interesting one. Let X be the closed vertical strip in R2, lying between the y-axis and the line. X equals 1/1/2 pi. So this is X. I'll just put on the outside X 1/2 pi. Or maybe it's 1/2 pi. Can't tell with the way that he writes things.
I think it's 1/2 pi.
Yeah, I think it's 1/2 pi.
Yeah.
Okay.
Because then when he puts that into the 1/x, it makes it
Right.
a
Yeah,
sine of
that's
2
right.
pi.
Okay, so he says let x1 equal. So there's a union going on here. 0y such that y is greater than or equal to -1.
Huh.
Union.
What is that?
So that's like
X equals
this
0.
line, this like
Right.
line right here.
Okay.
Okay. Union
So that's
X,
your
Y.
that's the
such that
well
x is between 0 and
I guess X1's not that X1's that vertical ray and
yeah, this is the first part of it.
you're working on the other half of it, yeah.
And y is greater than or equal to sine of 1/x. Very strange stuff right here. So sine of
Ooh.
1/x, if you'll recall, it's
Yeah.
like pretty messed up.
It's the
yeah.
yeah,
It's like that, and so x1 is this union, everything that's up here.
Yeah. Oh,
Okay.
why?
And x2
Why
is
so
equal
complicated
to,
in this example?
it's pretty similar to 0y, such that y less than or equal to 1. Oh man.
I've got a red marker somewhere you could use for the other one.
Do you want?
Or whatever green is. It would be more fun if you.
Yeah, I'll just use green. x2 equals 0y, such that y less than or equal to 1. Union xy, such that same as before. And y less than or equal to that's not how it works. Okay, so that is going to be.
Everything below that awful thing. So it's like.
I'll put this.
So I guess the intersection between these two things is just.
Okay. Then we also have everything less.
Oh, yeah.
And so we can see that this the green union of purple is equal to all of x.
So the intersection's like the. It's like the unit interval from -1 to 1 on the y-axis, and then just
and sine 1/x.
the awful sine curve.
Mm-hmm.
Why?
So
Why has he done this to
x is
us?
equal to x1 union x2.
I think you could find a simpler example.
Yeah.
There must be something.
But I mean, it's like.
There must be something interesting about this example. There's a reason he's doing this. Yeah.
x1 intersect x2 is equal to the sine 1/x space. So, yeah, like we said, sine 1/x, and then this -1 to 1. Okay.
So he calls the graph of sine y equals sine of 1/x unioned with -1 to 1 the sine of 1/x space, I guess.
Mm-hmm. So if Mayor Viatoris were
I
true,
talked about that before in the path connected stuff.
then there would be so if
We went too fast.
if this were true, then there would be an exact sequence
Huh.
h1 of x to h naught x1 intersect x2 to h naught x1 direct sum h naught x2 h naught x to 0. Okay, sorry about that. But, screen.
Huh.
Yeah, we can compute these. X, x1, and x2 are all contractible. So h1 of x equals h. Yeah, so all these are going to be 0, I think. Hopefully that's equals 0.
But you only run into h1 of x, I guess.
Right,
You don't
yeah,
run into.
exactly.
Yeah.
And h naught of x is equal to z, which is equal to h naught of x1 and x2. Alright. So that gives us this exact sequence. 0 to
Eh.
z direct sum z to z direct sum z again. Z to 0. Okay. Which contradicts exercise 5.5, which says that the rank of the second one has to be equal to the rank of the first plus the rank of the third. It's clearly not true because it's rank 2, rank 2, rank 1. There you have it. So this explains why having that is important. Okay, so let's get to a corollary of Mary. Too much.
Oh, that was the point.
What was the point?
That's why I was to get something complicated.
Counterexamples, I guess you could
Yeah.
show.
Okay. Yeah.
So I guess, okay. This is for the Torus Furries homology. Okay, so if you have x1, x2 subspaces with x equals x1, same as before, union of the interiors, and these are actually disjoint. Oh wait, they're not disjoint, just kidding. Then there exists an exact sequence. H and tilde x intersect x1 intersect x2 h and tilde x1. This looks very similar to the regular Merivy torus. X2. And that goes to 0. Oh wait, sorry, just keeps going. Okay, so it's pretty much the same thing as regular Merivy torus, but with reduced homology. And so, if you guys remember, the reduced homology is pretty much the same thing except oh, sorry. With induced maps as in the Merivy torus theorem, the sequence ends Alright, so yeah, so it ends like that. Oh right, okay. So this proof is pretty much the same thing, except we do change a few things. Because we're dealing with reduced homologies. Remember that we proved in section 5 that hn tilde of x is equal to hn tilde of x comma x naught. Right, okay, so we have similar to the diagram that we have on this board here. We have x1 intersects x2 comma x1, sorry, x naught. x1 comma x naught. So the inclusions are all pretty similar. Except instead of the empty set we have x naught. Yeah, so it's pretty much the same as the regular torus, I think. So. Yeah, because of this fact. Alright, yeah, I think that's everything's for that, so now we're getting to some applications.
Yeah. Check out Nathan. Applied mathematics.
Yeah.
We're applying math to math, right?
It works.
Still counts.
Pretty sure, engineers use the fact that the homologies of the different spheres are different
There.
all the time.
There are algebraic topology books which show how to solve circuits using cohomology calculations.
Interesting.
Yeah.
We got SN sphere,
Why I don't know.
n greater than or equal to 0. Then HP, okay, that's not, is equal to approximately if P is equal to 0 or 0 P is greater than 0.
So you're writing down the Pth homology group of the n sphere, huh?
Yes, so we have it for the 0 sphere, but we also have it for just a regular n sphere prime greater than 0. So we got that's equal to.
So the 0 sphere is the set of antipodal points, right?
Yeah.
Oh, I see now. That's an S sub 0. Sorry. My bad.
That's okay. Alright, and then this is equivalent to, uses a remark, but it's actually like how he proves it. The reduced homology of Sn is equal to Z if P is equal to N and 0 P is different than N for all N greater than 0. Okay, alright, so let's jump into that proof. So he does an induction. Okay, so it says, we do an induction on n greater than or equal to 0 that HP of Sn is as claimed for all p greater than or equal to 0. Okay, so for n equals 0, induction. We have, oh, out by the dimension axiom. Recall what the dimension axiom is. So that theorem 4.12. Right. Because wait, hold on. So dimension axiom is for a 1-point space. This is 2 points, so I'm trying to remember this here. All right, since it's since S naught is equal to -1 union or direct sum. Well, okay, I don't know what it is. I can, yeah, so the homotopy, or sorry, the homology of S naught is going to be the homology of -1, or of these 1-point spaces. Which is just going to be 0, because by the dimension axiom, the homology of both of these is going to be
so
0.
that's where he's using the
For all p greater than
4.13 to break it to the direct sum.
That's HP for p greater than 0. Okay.
Certainly. -1 path components for S naught. Yeah.
What'd you say?
Certainly -1 and 1 are path components for S naught,
Yeah.
which is what you were using there. Yeah.
Yes. All right, and so for n greater than 0.
Now you're inducting.
Yeah.
Are
I'll
you
say
still-
n equals p, or not p, n equals k, let's say. So assuming it to be true. So that means that HP of SK is equal to Z B is equal to. Oh yeah. Oh yeah. Okay, so let A be the north and south poles, and let X1. Maybe I should write that. North and south poles. That's good. Okay. Then let X1 equal to SK minus A. X2 equals SK minus V. And so SK is equal to the union.
So what's the interior of that? I guess it's just, oh, they're open, aren't they?
Yeah, they're open.
And their union's definitely the whole
Yeah.
sphere.
And they're both contractible.
Yeah. Huh.
So, for example, if you wanted to draw pictures for like the two-sphere versus